Professor Margulis, firstly, we want to congratulate you on being awarded the Abel Prize 2020, together with Professor Hillel Furstenberg, for your, and we quote, pioneering the use of methods from probability and dynamics in group theory, number theory, and combinatorics.
It's a great honor.
Very briefly, and we'll come back to the background story in a moment, but just to place your mathematics, you've mentioned when you received the Wolf Prize that was for contributions in algebra. Your NSF grants have been to analysis, and the Abel Prize seemed to focus mostly on probability. So where should we place you? What type of problems attracts you?
Yeah, no, so actually when I wrote you, I said that in a sense, I mostly consider myself to be a geometer. And actually, I mentioned it when I wrote to you that once I talked to Jacques Tits on the phone about someone else, he said about himself that I am a geometer and you are a geometer. So it's probably it's somehow I am a geometer in a sense that it's kind of mostly based on imagination or something. There's a different types of geometers.
Okay, let's see whether we can get back to geometry as we go along. Of course, Tits is a previous winner of the Abel Prize. In your early life, when did your interest in mathematics start?
Yeah, probably from some early age. So my father was also a mathematician, but he was mostly interested in mathematical education, and he wrote his PhD or candidate thesis under the direction of Hinchin, who was a famous probabilist. But my father's dissertation was on education. He was how it's called, candidate of pedagogical sciences.
Ah, I see. And you played chess, and you were included in mathematical circles run by the Moscow University. What was life for you as a kid in Moscow in around 1960?
Yeah, no, so it's hard to describe. So it was okay. So it's, in a sense, so my family was relatively well off. So my father was working as in institutes, educational institutes, and his salary was relatively high compared to average salary, and we, from quite early time, still from the time when I was 7 or 8, we had our own apartment, it was in 54, which was quite exceptional at that time. So people usually lived in some so-called communal apartments. So there's a family occupied a room, and there was several families in one apartment, and so but yeah, otherwise it's okay. So I believe that my father actually encouraged me to do mathematics, so he probably realized that I have some something to.
So it was natural that you were included in these mathematical circles?
No, it was not included. Somehow there was no any competition to. No, but mathematical circles were starting from the 7th grade, so it was probably I was 12 or 13 at the time. But okay, I probably from quite early age. Okay, I couldn't multiply double-digit numbers, so which is.
Was it tough being in the circle? Was that hard work?
No. Circles, okay. No, it was rather informal, so I don't remember many details, but there were, so it were run by students, or maybe sometimes graduate students from Moscow universities, and discuss various problems and encouraged to solve them. And yeah, there was also some supervision by a more senior mathematician. Yeah, no, so also somehow at that time, mathematical Olympiads were quite connected to these mathematical circles. And
So that was natural to participate in the Olympiads.
yeah. So it was, yeah, it was in Moscow. I think it was in the City Olympiad, and probably so-called for the entire country. Probably it started later, but probably about the same time. But somehow it was mostly in city, just in the city, and somehow there was no any competition to enter. But somehow maybe it was quite challenging for many. So it's maybe.
But I can imagine you did quite well.
Yes.
So we'll return to your mathematics in a moment, but perhaps first we should talk a wee bit about your early career. You write your first mathematical paper before you're 20, and in 1970 you and your fellow student Kazhdan published a very influential paper. How did that play a role in your later life, for instance, towards arithmeticity and so forth?
Yeah, so my first paper was done in Dinkin seminar, and it was about positive harmonic functions on nilpotent groups, and probably it still has some influence now even. But the paper with Kazhdan somehow starting with this paper. Okay, the paper was about the existence of unipotent elements in non-uniform lattices, and somehow the title was The Proof of Selberg's Conjecture, which is probably Selberg stated this as a conjecture. But it was directed to the proof of the arithmeticity of non-uniform lattices in semisimple groups. So actually this paper with Kazhdan somehow was starting points to working towards the proofs of the arithmeticity.
Rest assured that we'll talk more about that. But it seems that caused some stir. Borel mentioned it in Bonn, but you went on to the Institute for Problems in Information Transmission, and according to problems in information transmission, and according to Dinkin, who you mentioned, what he actually says is you must have had the luxury of spending most of your time to your own research. Is that a fair assessment?
Yes, it's quite a fair assessment. So actually maybe, I didn't get a position, let's say, at Moscow University or Stiklov Institute, but this Institute of Problems in Information Transmission was one of the institutes of the Soviet Academy of Sciences. By Soviet standards of that time, institute was relatively small, but only 200 researchers. But by Western standards, it's probably would be considered a huge institution. And I worked. My immediate boss was Dobrushin, who is a famous probabilist and mathematical physicist, and also there was another related group which was headed by Mark Pinsker, who is, was famous in information theory. And so, and in a sense, probably it was I was in some lucky to be there because probably my most say famous or well-known work, it was on expanders, was done there, and then just because I was, Mark Pinsker was close there, and also some other people.
But you must have done other work there as well, leading up to, well, we're not far, it's not long until you win the Fields Medal here.
Yeah, so, but this is somehow, in a sense, this work on expanders and somewhat else was done in some sense under pressure. But also I considered that mostly working on discrete subgroups of Lie groups and this arithmeticity and superrigidity and so on, but it was done kind of in parallel. But probably most of my time was dedicated to some kind of my kind of own independent research, so maybe not quite related to the main direction of the institute.
While you were a student at Moscow University, you attended Dinkin's seminar. When you wrote your PhD thesis, it was under your advisor was Sinai. Can you tell which mathematician influenced you the most when you were a student at Moscow University?
It was Sinai. It was. So I mentioned about work on discrete subgroup of Lie groups, but probably before that I was I attended this Sinai seminar in dynamical systems. Was run by Sinai and Alexeyev, and probably some. So after this first work on positive harmonic functions, I did actually two works which are related to dynamical systems. One of about the annals of systems on compact free manifolds, some about the conditions on the fundamental group, and another about counting of closed geodesics on compact manifold of negative curvature. And it was done because I was close to the seminar. And Sinai became my advisor starting probably it was third year of my undergraduate studies.
But if you should rank the people that influenced the most while you were in Moscow, would you rank, who would you say had the most influence upon your mathematics, your research?
So of course Sinai, then after that was, there's a Petetsky Shapiro somehow, then my fellow, and there's a classmate, David Kazhdan, he was Dima Kazhdan in Soviet Union, now he's David Kazhdan.
Yes.
And so also there's a Winberg for the work on discrete subgroups of Lie groups, who passed away recently. And but also somehow the probably many other people.
But did Piatetsky Shapiro make you aware of his conjecture and Selberg's conjecture about lattices in semisimple Lie groups? Did you get the problem from them?
In a sense. So there was, there was this Selberg, probably Selberg, and started with Selberg and Petetsky Shapiro. So Selberg was So actually, he maybe stated the conjecture only for non-uniform lattices, And for uniform lattices, actually, he didn't have a definition of an arithmetic subgroup, and it was done by Pitsetsky-Shapiro. So it's, so this problem somehow circulated in, mostly probably due to Pitsetsky-Shapiro, and so also, so initially was from him, and he, in a sense, so I first proof for non-uniform lattices, following the strategy which probably it's in some due to Selberg and Pitsetsky-Shapiro, it's starting with unipotent elements and then do various actually quite complicated technical work, but
you know, when you got the Fields Medal in 1978 in Helsinki, then Jacques Tits wrote about your achievements, and he bragged, that's a mild word, about your technique to prove this result on the arithmeticity of lattices, Could you comment on how long time did you use on that proof, and what was the main ingredients in your proof?
So again, one is maybe it's better to split this in two parts. One is about non-uniform lattices, and this was more or less strategy was kind of known, but for certain subgroups, it's essentially had been done by Selberg and Pitsetsky-Shapiro, but for general case it was technically much more complicated. But then for uniform lattices, actually, in a sense, there was no strategy. And at some point, so actually for non-uniform lattices, it took for me quite a long time to write a detailed proof. So it took 2 or 3 years.
I'm sorry, when were you finished with the uniform lattice proof?
For non-uniform?
No, the uniform.
No, I know about non-uniform it was no more or less some kind of crucial step. There was an announcement in 1969, then I wrote quite a long paper about this crucial step. It was in 71, but because of some difficulties in publishing, it was published only in 75. And then it's from this crucial step to go to full arithmeticity, probably it was, again, 73 or 74. But about uniform lattices, so some probably it was in 69 or 70, I learned about work of Mostow on strong rigidity. And at some point I realized that maybe there was an approach to prove arithmeticity using some more general statement than strong rigidity, which was later called superrigidity. And actually, also this realization was kind of original. So. And then to prove superrigidity, so it's proof of Mostow was mostly based on kind of geometric and topological arguments, but somehow it could not be immediately generalized to the superrigidity. And at some point I realized that it's some kind of ergodic theory, measure theory, multiplicity ergodic theorem can be applied to prove that. And so it's involved and also some results from representation theory. So it involves methods which are actually quite far away from kind of original formulation of arithmeticity.
So is it fair to say that your strategies for the non-uniform case and for the uniform case, they are vastly different?
Yeah, they're vastly different. Yeah, it's for non-uniform case, there's there's unipotent elements, and there's some kind of building blocks of which allow to somehow to get the structure of arithmetic groups. For uniform lattices, somehow there's no kind of building blocks. So it's for non-uniform lattices, it's mostly algebraic and maybe some geometry, but for uniform lattices, have to use transcendental methods.
To get back to the uniform lattice case, I remember I was present at the Selberg Fest in 1987 in Oslo.
Yeah, I was also there.
And I remember Mostov introduced you in glowing terms about your achievements. And he said something to the effect that, well, you proved it, this superrigidity theorem, by consisting of a succession of extraordinarily ingenious argument using a great variety of very strong techniques belonging to ergodic theory, for instance. Could you comment more about how ergodic theory was involved in this proof of the uniform case?
Yeah, no, so it's probably I cannot do this in any detail, but at some point I realized that there's a multiplicative ergodic theorem of oscillators can be used, but probably it would be difficult to explain this.
But we've made one sin, and that is when we started talking about this without actually discussing what is arithmeticity. So why? Could you explain that to us?
Yeah, no, so it's arithmeticity. Yeah, no, so there's if one consider group of SL and R, the group of unimodular n by n real matrices, and consider subgroup there, SL and Z. So it's subgroup which consists of matrices with integral coefficients. And so this is kind of the most standard example of an arithmetic subgroup. And so there's a classical statement that SL and Z has finite co-volume in SL and R. It probably goes back to Hermite, Minkowski. But even Harish-Chandra generalized this to semisimple groups. So G of Z has a lattice that has a finite co-volume in G of R, where G is a, say, semisimple group. And so this is, now it's problem of arithmeticity that under certain conditions, this any lattice any reducible lattice in a higher n group is arithmetic, but you need to extend the definition of arithmetic subgroup, and so one extension is to commensurable with G of Z, but then another extension was actually due to Petetsky-Shapiro. There's some construction which comes from maybe a bigger group, which maps into the original group with compact kernel. So it's, I actually probably Selberg didn't know this definition, but it's.
Could you comment on your colleague Furstenberg, who also got the Abel Prize for the 2020? There is another proof, quite different proof of the superrigidity theorem that came late after your proof, and its application to arithmeticity, both in the co-compact and the non-co-compact case, being the work of Furstenberg. Isn't that true?
Yeah, no, so it's, yeah, there was a, yeah, no, so my proof was for co-compact case, okay, for non-co-compact case, somehow I had this proof of arithmeticity before by a completely different method. For co-compact case, yeah, there was actually two parts in the proof. There's just existence of equivariant measurable maps, and the second is rationality of these equivariant measurable maps. So it's for the first part, so it's, okay, I did this for co-compact case, and also under certain integrability conditions, which for certain cocycles, it can be extended to non-co-compact case. And actually, I could do that, but for this I had to use this previous, the proof of arithmeticity and some estimates. And Furstenberg gave some, for this part of existence of equivariant measurable maps, he gave a different proof, which actually is not exactly, so it's not based on multiplicative ergodic theorem, but on boundary theory, his boundary theory, which is, in a sense, quite related to this multiplicative ergodic theorem. Actually, one of the origins of this multiplicative ergodic theorem of oscillators was previous work of Furstenberg and Kazhdan.
Can I follow up on that? Because as far as I understand, you learned about Furstenberg's work, around 74, the boundary theory, and that goes into your normal subgroup theorem, which proof you actually have stated is, you think of as your best proof. And actually, I think the statement is awesome as well. Could you please tell us first what the normal subgroup theorem says, and then why the proof is so good?
Okay, so it's, yeah, the normal subgroup theorem is, okay, so if you have a semisimple group of higher rank, so without compact factors, rank is at least 2, and if we have an irreducible lattice, then any normal subgroup in this lattice either belongs to the center of the group or has a finite index. So it's a special case, for example, if you take SL3R, so 3 by 3 matrices, and take a discrete subgroup which has a finite covolume there, then the statement is true that any normal subgroup in this lattice should be either central or has finite index. The proof is actually divided in two parts. So you have this lattice gamma, and then you have a normal subgroup N. And there's two parts. One is, consider gamma by N. So the first part is that it's, so if the quotient is amenable, so there's a notion of amenable group in this group theory, then it's, this quotient should be finite. And this is mostly based on the Kazhdan's property T. Now in our case, it's, and essentially it had been, but in another it was that gamma by n is non-amenable, and then it's, somehow I realized that one can use so algebras of measurable sets, and this somehow one of the basic tools was this, one of the initial lemmas in Furstenberg theory. But for example, for the proof of superrigidity, in some sense I can maybe explain how I came to that. So I look at most of those proofs, so it didn't work, but then for this proof of that if it's non-amenable, then it should be central, and somehow it's, actually I cannot explain how I came to that. It was some kind of intuition, and that's, and so also the idea to subdivide this proof in two parts was probably quite new, but somehow I consider the best proof that actually, because it's mostly based on intuition. And
were there any precursors, or did this come out of the blue to you, the statement of the normal subgroup theorem?
The state of normal subgroup theorem somehow, in some sense, was, in certain cases, was known, but somehow this, especially for the SL and Z, and so but it was done by algebraic methods. But for co-compact case, it was, for the NSL 3I and co-compact lattices there, it's, and so maybe it was natural to assume that it's true, but somehow this approach with using, again, measure theory. For example, one of the ingredients in the proof is the density point theorem in measure theory, which is, so it's, actually, so there's a algebraic statement of the theorem, and the proof is completely mostly non-algebraic.
So, so jumping a wee bit, but another example where you prove stuff that belongs perhaps in algebra by your sort of methods, which to me at least are very surprising, was when you proved the Oppenheim conjecture. Could you explain to us what that is and how we should think about it?
No, Oppenheim conjecture is actually quite natural conjecture. So there is a classical Myers theorem which says that if you have an indefinite rational form in at least 5 variables, indefinite, then it's non-trivially represents 0 of a rational number. So if you have the Q is this form, then there is a non-zero integral vector, then vector x, that Q of x is 0. And Oppenheim, he was a student, he was British, and he was a student of Dixon in Chicago, and he worked actually on this rational forms in 4 variables, and he published a paper in probably Proceedings of the National Academy of Sciences. It was about 1929 or 1930, and there was a footnote where he formulated the conjecture, which can be considered as an analog of this Myers theorem for irrational forms. So we have a Q is an irrational form in at least 5 variables, indefinite. Then for every positive epsilon, there exists an integral vector x such that Q, absolute value of Q of x is less than epsilon.
So the image of the integers is dense, is what you're saying?
Yeah, it's more or less, it is slightly stronger, but it's mostly, yeah, maybe it's also possible to. Later on it was kind of realized that the conjecture could be strengthened. Now there was quite a lot of work on using analytic number theory methods, and the main progress had been done by Davenport and his co-authors, starting from 1946, going to 1959, where they proved this for number of variables, at least 21. But it was some mostly analytic number theory methods. Now in mid-70s, M.S. Raghunathan realized that it could be, actually also Davenport realized that it could be not starting just from dimension 5, but for irrational form, but starting with dimension 3. For dimension 3 and 4, the statement of Myers' theorem is not true for rational forms, but for irrational forms it's true. But so Raghunathan realized that certain the statement, Oppenheim conjecture, can be reformulated as some dynamical system, as a statement in dynamical systems, so which is
in your ballpark.
If you have SL3I and SL3Z, and if you take, so G is SL3I, gamma is SL3Z, and if you take SO21 group H, then any bounded orbits under H in G mod gamma should be closed. And actually one particular case of the Oppenheim conjecture, for example, can be stated for very special case. If you take this form Q, which is x squared plus y squared minus square root of 2 of z squared, then if you take this form and take Q of z free, then it should be dense in R. And the proof of this special case is not any simpler than in general.
But you learned of this problem in Bonn, I understand?
Yeah, I visited Bonn for 3 months. I was born in '79, probably for 3 months from the beginning of July, and I met Gopal Prasad, who was a student of Raghunathan. Now he's a well-known mathematician, and
you came with the proof was published at least in '86.
Yeah, in '86, but probably already in I remember already in '84 I gave some kind of oral presentations about.
Before we leave this period of your math, I have to cite or quote what Jacques Tits said at the ICM meeting in Helsinki when you received the Fields Medal, even though you were not allowed to participate. He said the following: Margulis has completely, or almost completely, solved a number of important problems in the theory of discrete subgroups of Lie groups, problems whose root lies deep in the past and whose relevance goes far beyond that theory itself. It is not exaggerated to say that on several occasions he has bewildered the experts by solving questions which appeared to be completely out of reach at the time. I think this is a wonderful acknowledgement of your contribution up to when you got the Fields Medal. You don't have to comment on that.
Yeah. No, so probably I already mentioned that for arithmeticity for co-compact lattices somehow.
But the Tits sort of puts it in a context and says this is bewildered people because people didn't think it was within reach.
Yeah, no, so it's okay. It's probably I'm not the right person to comment on that. But,
No, exactly.
but I think Dennis Sullivan mentioned to me several times when Jacques Tits gave a presentation, probably in an IHS about my work on the proof of co-compact lattices, and it was involved ergodic theory, and somehow probably say Herman Barrel was extremely surprised that there is some arithmetic statement. What is the relation with ergodic theory? And again, you can check with Sullivan, but he told me that on the way to this, from Paris to IHS, he explained some basic notions of ergodic theory to people who were with him.
Let's move on to what we briefly mentioned before, namely expander graphs. And you said that while you were, was it Pinskner that sort of introduced you to this topic, expander graphs? Can you tell us, first of all, what is an expander graph?
Yeah, no, so it's this notion was introduced by Mark Pinsker here in his work on concentrators and some construction of concentrators. Now there's some canonical definitions, but basically it's one of the, probably it was not the original definition of Pinsker, but say probably in most textbooks on expanders, so it's you have a regular graph with finite graph with non-oriented with n vertices, and it's a regular graph from each vertex. Say we have certain, let's say 5 edges, and if you take any subset of vertices which has less than n over 2 elements, so m vertices, then they're connected to m multiplied by 1 plus epsilon other vertices. So actually the definition is not just for one graph, but for infinite family of graphs. So the set is expands to some bigger set. So it's started with work of Pinsker, but then he proved the existence of this using some probabilistic methods that under certain constructions, almost all graphs which come from this construction are expanders. But there was no explicit construction, and I more or less realized that using something like group theory and especially property T, or some maybe some weaker statements, you can construct this family. And probably it was kind of unexpected for people in computer science.
And later on you constructed even more examples of expanders, isn't that correct?
Yeah, so later on there was this graphs which came from quaternions, and actually it was 1984, and I was mostly interested in this graphs. And again, there was some construction, probabilistic construction due to Erdős and someone else, and so you have a regular graph, and then it's with n vertices and regularity, say p. Then it should be the upper estimate for the graph is 2 log n model log p n, and the existence was log p n, and the construction, explicit construction, was quite surprising. It was 4/5 of the log p n. And I believe that until now, actually, there are no even probabilistic constructions which go beyond log Pn. And there are also, about the same time, I realized that they also give some expanders, but based on some work of Deligne. And slightly later, and completely independently, Lobotski, Phillips, and Sarnak essentially gave, so basically the same construction, but some variations, and also they used, work of Deligne and this extremely advanced mathematics, and they use something maybe less advanced, but so Lobotski, Phillips, and Sarnak, and they quote these graphs which have come with this construction, Ramanujan graphs, because it's related to some Ramanujan conjecture.
Moving on to another problem that you solved in, this was in the very beginning of the 80s, and I quote the Mathematical Reviews, which says that although it is not explicitly stated, this paper settles a long-standing problem of Banach on the uniqueness of invariant means on the n-sphere. I understand that this came to you in a flash, and it involves property T again. Could you tell us a wee bit about the story behind this?
Yeah, the story, so I believe I was in a conference in Poland. I met Rindler, who Austrian mathematician, and he mentioned this problem of Banach and Rushevich about invariant means for algebra of measurable sets, and then he said that there was a kind of work of Rosenblatt who kind of reformulated this in terms of, or just explained that it would follow from the statement about small, almost invariant sets, and more or less I immediately realized that this statement can be deduced deduced from property T for certain subgroups. So it's, if you have a S, okay, it was starting with dimension 5. So if you have, let's say, S of 5, then it contains certain arithmetic lattice or S arithmetic lattice, and it has property T. So I think essentially at the same time, and probably following, again, using work of Rosenblatt, Dennis Sullivan did, he used slightly different subgroup, but it's basic. So it's actually it was came to me almost immediately, maybe.
Is this typical? Does this happen to you from time to time, that you all of a sudden just see the answer?
No, maybe not. Maybe I had an answer before I had a question.
Fair enough.
No, but no, actually, it's okay. So this work became quite famous, but actually, I didn't spend much time on that.
That's fair enough. So just one thing. Can I ask you about your work style? Because there's one thing that strikes me, and this has nothing to do with your theorems or whatnot, but early in your career, next to all your papers are one-author papers. And then the last 30 years, next to all of them are joint papers. Is that something that happened to you, or is it you moved to a different environment, or how would you explain that?
Yeah, no, so it's so actually this was before I moved to the West. So okay, when I was in Moscow, I think essentially almost all my papers were just written by myself. Okay, there was a paper of Kazhdan, and maybe it was, and actually for me it was somehow quite challenging to write papers, so it's probably I didn't. Yeah, okay, it took a lot of time. But when I moved to United States and to Yale, okay, it was, of course, completely different environments. I started to work with many mathematicians, probably mostly younger than me, and also started to work with graduate students. And
was that fun? Did you enjoy it?
yeah, well, working with graduate students, it was actually, this is what I didn't have in Moscow. And okay, I had I was a physics advisor for Seufert, but somehow it was in some sense accidental. So actually he was not, I was his physics advisor, but he was not my graduate students. But when I moved to Yale, so it's actually it was not guaranteed that I would have graduate students, but somehow I find it very rewarding.
And I noticed that even in last year, 2019, you have a paper together with Amir Muhammadi. So this goes on. You're still working with younger fellows.
No, yeah, Amir Muhammadi was he was my graduate student, but it was probably, he's now close to 40. Probably he finished more than 10 years ago. And I had I had a joint paper with him when he was a graduate student, and then several papers after that. Yeah, so now I retired, so I had my last student finished this calendar year. But yeah, so Yeah, no, it's hard to tell. Okay, so now it's different times, so it's...
Yeah, it's true.
Okay, well, that brings us to the end of the interview. We want to thank you on behalf of the Norwegian Math Society and the European Math Society, and on behalf of Björn and me, for a very interesting interview. Thank you very much.
Okay, thank you.